So here's part 6 of question 4, and just as we left off in part 5, we have that f of x1 times f of xn, or f of x2 all the way till f of xn is equal to e to the t times s, as it's given in the question, right? So now we have this has been defined as y. Alright, so actually I should make that more explicit. So we have y is equal to definition is equal to e to the ts. So first of all, the question asks, does it always take positive values? So as long as t and s are both real numbers, if you take e to the something which is a real number, it's always going to be positive. So yes, always greater than 0. It also doesn't take the value 0 unless the exponent is negative infinity, and since we're only dealing with the set of all real numbers, that never comes. That's never the case. So now we want to bound the probability of what? We want to bound the probability that s is greater than equal to. So we want to bound the probability of s greater than equal to 1 plus alpha times the mean mu. So and alpha is a non-negative integer. So we want to prove that, first of all, we want to prove that the events, this is equivalent to, or rather this is the same. I'm going to talk about events now. Prove that s greater than plus alpha times mu if and only if y greater than equal to e to the t mu plus times 1 plus alpha. So what is y? Y is e to the ts. So this is if and only if e to the ts, because I'm just going to replace y with the definition, greater than equal to e to the t mu 1 plus alpha. So the only thing to note here is that since the exponential function is a monotonically increasing function, and what that basically means is that if you have two values a and b, a greater than equal to b if and only if e to the a greater than equal to e to the b. So since the exponential function is monotonically increasing, this holds true. So you have, just by this property, e to the ts is greater than equal to e to the t times a mu or times 1 plus alpha. It happens only if and only if s is greater than equal to 1 plus alpha times mu. But there is a caveat here. This requires t to be greater than equal to 0, not greater than equal to greater than 0. Right? And as we will see later, t will be greater than 0, so this is fine. If t is less than 0, then the inequality sign is flipped, because now you have a negative as the exponent, and if you increase the negativeness, then it's obviously going to decrease the value of the exponential. Now we want to use Markov's inequality to find a bound on the probability of, so we have this is equal to probability, we just proved that the events are the same, therefore this is equal to probability of 1 plus alpha times, e to the, I'm going to take this off, e to the t mu times 1 plus alpha. So we just proved that the events are the same, therefore the probability of those two events are the same. So now we want to find a bound on this thing using Markov's inequality. So how do we use Markov's inequality there? Probability of y greater than equal to e to the t mu times 1 plus alpha is equal to expectation of y divided by e to the t mu times 1 plus alpha. Right? That's what Markov's inequality states, which is equal to e to the expectation of e to the ts divided by e to the t mu times 1 plus alpha. Now this, I think, which we showed in the previous question, okay, this is equal to expectation of e to the t times x1 all the way till xn to the t mu 1 plus alpha. This, as we showed in the previous question, is just less than equal to e to the, this is Markov's inequality. It's definitely not equal to, it's less than equal to. So yeah, this expression here is less than equal to e to the mu times e to the t minus 1 divided by e to the 1 plus alpha t times 1 plus alpha mu, which is equal to e to the, let's put the whole thing, or let's make it easier. Just for this place, I'm going to write it as exponential of mu times e to the t minus 1 minus t times 1 plus alpha times mu. So yeah, I could pull the mu out, but yeah, you get the point. So this is the bound which we get on this probability using Markov's inequality.